Hello friends, welcome to Truth of Physics. Today in this particular video, I will detailedly discuss on what is mean by computable observables, that is the commutation bracket of two observables, suppose A and B is equals to 0. Then it is known as commutation bracket, we know that. Then if this commutation bracket is equals to 0, then we call these two operators observables to be computable observables, okay? And there is a theorem like this which states that if we have two computable observables like this, then the eigenvalues of, and if we assume for the initial case that the eigenvalues of A is non-degenerate, okay? Later in this video I will discuss the case for degenerate case also, but initially we are assuming that A has not A are the eigenvalues of A are non-degenerate, okay? Then the matrix elements, these are all diagonal. That means the B matrix, right? Operator means what? In quantum mechanics, we always represent an operator with a matrix, right? So this matrix will always be diagonal, right? We have to prove that. And later, and there is another statement like this, that the operator A is already diagonal if this this A dash ket A dash are used as baskets. So what these things are really mean, we'll discuss in this video. Now, what is this thing means, right? This statement. We know that an operator, we always write or always express an operator or a matrix with some basket, right? Now if we use and the matrix elements of A operator looks like this, right? This is the matrix elements. Basically the matrix of A or operator A can be written like this: A double dash, and there is A. Now use the completeness, double summation here. One is A dash, one is A double dash. Now this is nothing but our A operator, right? And we know that we know that completeness, from completeness theorem you can know, you know that this is nothing but identity, this is nothing but identity. So we'll get A operator. Now this thing, this part is the matrix elements. That means the matrix elements of A operator is like this. Now if these baskets with which the operator A is defined or is expressed, right, these are what? Baskets. If these baskets like A dash comma A double dash, these are baskets. If these baskets are the eigenkets of the operator A, eigenkets means this thing, mathematically some eigenvalue lambda into this, right? We'll get back, when we apply this operator on this eigenket, we'll get back the same eigenket with an eigenvalue, a number basically. That means then if these are the eigenkets of this operator, then it is very simple. This matrix becomes very simple. Why? Because then it will act on, because this means what? This means what? This means actually A, this thing, right? Then first it will operate on this and give the things like this. That means some constant. Suppose the eigen value is A dash itself, then it will become like this, and it will give back this thing, right? It will give back this thing. And from the orthogonality relation of the eigenkets, right, the eigenkets are orthogonal. That means that this thing is nothing but the Kronecker delta A dash A double dash. Means whenever A dash and A double dash is equal, then only this value will be A dash, and otherwise this will not give you any value. That means this will be 0. Basically that means that A dash is equals to A double dash whenever, that means the matrix, if we represent it in terms of matrix, then we know that this matrix will look like something like this: A1 into A1, then A1 this is A1, and this is a1, a2, right? And there is the eigenvalue here. Here is the eigenvalue a2, and this way, right? And there is this thing. So what this means that these terms always vanish because of the orthogonal property of eigenkets, and these terms also vanish. Only the diagonal terms will be 1, will give us value, right? This is 1, that means this is a1. Similarly, this diagonal 2 comma 2 point will give a2. Similarly, this will be a3, a4, and all the diagonal terms will be valid, will be there, and all the off diagonal terms, not only off diagonal, all the other terms will vanish. That means this basically means that this will be diagonalized. This matrix A will be diagonal, and when this matrix A will be diagonal, when we can express this matrix with with the base kits to be the eigenkets of the operator itself, means these are the eigenkets of A, then the A matrix will always be diagonal. Okay, now the question here is, if we have two operators like A comma B, and the commutation bracket is 0, then we can also say that the B operator, we know nothing about B, but we know this relation. Then we can prove that B operator can also be diagonalized with the same set of eigenkets, that is the eigenkets of A. That means mathematically I can write this will be equals to 0. What this means actually is B can be, or B is an eigen, B can be diagonalized with this eigenkets, right, with the eigenket of A. That means if we apply B operator on A dash eigen vector, then we'll get back some another uh, eigenvalue like B, and we get back the same eigenket. How this happens, let us understand that with the proof of the above statement, right? This statement. Okay, now what this statement actually means, if we have A comma B equals to 0, then what happens, we express it in terms of the matrix elements of this, that will give like this: A comma B, this commutation, and then A dash, which is equals to 0. And if we apply the property A comma B, its commutation is nothing but AB minus BA, right? So now we actually have to prove this. Now we know that A dash operating on this will give, because this, what this means, this means A dash means A first operate on this, and then B will operate on that. So A will operate on this eigenket and give A dash eigenvalue, suppose, then it will give, then this part will give what, A dash, right, and then A double dash, B, and A dash, like this thing. Now we know that the dual correspondence of this thing is this, right? This is the dual correspondence, means its dual is this. Then I can write this like this. I can express this is equals to uh, this thing, right? Because when we do this operation, it will give, if we do this operation, then it will give what, this thing. We all know this. And if we have expression like this, then what is the answer? Its dual correspondence will be like this. This ket will be transformed into the bra, right, bra vector, like this, and this bra will be transformed to a ket, like this, and this operator will be daggered, right? AB, its whole dagger, means B dagger first and then A dagger, right? Why B dagger first? We'll later in discussing and some another video that how this becomes B dagger first and then A dagger. Okay, then its complex conjugate. So it will be equals to this, right? Then minus A double prime and B A and A prime. This thing. So now A dagger, if we apply A dagger on A double prime, then what will get? The complex conjugate of A double dash, right, into this thing, right? That means we will get from here, I am removing the and then this thing, right, and its whole complex conjugate, whole star. That means this thing will give you A double prime, because it's star and that star means nothing but A double prime, and then its star, right? Its star means this state will be transformed to bra and will come to first. That means A double prime and B dagger will be transformed to B and A prime minus this thing. A double prime, B A and then A prime. So now if you common this term, okay, here was say A prime, right? Here is A prime, because when you apply A on this eigenvalue, you will get some eigenvalue A dash. So A dash. So taking common, you can get things like this: A double prime B, and then sorry, there will not be A anymore. There will not be A because there will not be A, because A has already operated. A has already operated on this and give some eigenvalue A dash and the operator and the eigenvector back. So this will give this. Now you can easily understand that if our A dash, for the case of when our A double dash is not equals to A dash, then for this thing to be valid, because the left hand side is equals to 0, right? A comma B is equals to 0. We know that, right? A and B are computable. So the left hand side is equals to 0. So the right hand side, for this case, for A dash not equals to A double prime, for this case to happen, this thing must be equals to 0, means A double prime B and A prime, this must be equals to 0, means all the only the diagonal elements must be present there, because this means what? Whenever A dash is A prime is not equals to A double prime, means we are talking, what this means, we are talking about only the non-diagonal terms, right? All the terms except the diagonal terms, right? What we have discussed before. And for the case when A dash is equals to A double prime, then this is not necessary. Then this will not be equals to 0. Then we know that this contribution will give us the 0. So the left hand side will be equals to 0 also. So whenever, so this means that this we can write like a notation like this: the Kronecker delta A prime A double prime and this thing. This gives us all the diagonal elements, and this shows us that only the diagonal elements will be present there. So that means B matrix or B operator must be diagonalized. When we have a condition like this: A comma B is equals to 0 and A comma B is equals to 0. That is, A and B can simultaneously be diagonalized with the same set of eigenkets, which is the eigenket of A, right? Means you can understand, when we apply B operator on the eigenket of A, then what happens? B means, if we express B in terms of the eigenkets, means B operator the matrix form of B operator, then it will look like this: A double prime. It will look like this, right? This thing is this, and and this is the matrix element, right? This is the matrix element, and here you can see that all the indices are double prime because this B is now diagonalized, so I can represent it with a single thing, right? A double prime. There is only one summation. That means that what it means by orthogonality relation, this will hold only for the value of A double prime to be equals to A dash. Otherwise, this all thing will be equals to 0 because of this orthogonality, right? So this will expand, right? This summation will be expanded for several values of A double prime, and only for the value when A double prime is equals to A dash, we can get some result. We can get some value. That means it will give us things like this: when A double prime is equals to A, then we will get this, then this summation will be removed because there is only one value, and you will get the value A prime. This will come here, A prime, and this will be 1. So just look at this relation, this expression. This is what B operating on this eigenket will give some value. This is what some value, right, into this operator back, this eigenket back. That means this is the eigenvalue, right? This is the eigenvalue, and this is nothing but the eigenvalue equation. So the operator B also follow the eigenvalue equation with the same set of baskets, or with the same set of eigenvector of A, right? A operator's eigenvector. So mathematically we denote the state of both A and B, because both A and B are simultaneously diagonalized with the same set of eigen basis or eigenvector. Then we can write a general or a common eigenstate like this: A comma B, or something like this: A dash comma B dash, to represent the simultaneous eigenstate of the system. Now what this means actually, A operator acting on this joint, you can say joint eigenstate, right? Joint eigenstate, then it will give the eigenvalue this, and when B operator will operate on this same eigenstate, it will give this eigenvector, eigenvalue, and the eigenstate back. What I have discussed here is for non-degenerate case. Now we'll discuss for degenerate case. The things will be very simple here also. Now if you really understood these two things, then you can understand that for the non-degenerate case, if we sequentially do these things, like if we operate A operator on the eigenkate, then we will get some eigenvalue like this, and then after that we apply B operator on this and we get the eigenvalue B dash, and then again if we apply A operator on the eigenkate, then again I will get A dash. Why this happens? Because what this means actually, because this will happen only for this case, because A and B are compatible observables, means that A and B can simultaneously be diagonalized. Means what that means actually physically, that A and B can simultaneously be measured with 100% accuracy, right? Like you recall the uncertainty principle that X for a system, for a same system, if we measure X, then our momentum will be changed, right? Because because this uncertainty relation says us that it is not equals to 0, right? Means there will be some uncertainty in measuring the momentum p when we want to measure accurately the position of the state. But this will happen only for one system, right? For only say for system A. But if we measure the position of system A and then simultaneously if we measure the position the momentum of system B, then there is no um, sort of uncertainty, because these two systems are compatible, this thing, because the two systems are compatible observables. So these two things can simultaneously be measured or there is zero uncertainty. So if we measure a operator on, if we measure this thing, we will get something like this, some value this, and then sequentially if we operate B operator on the state eigengate, then we will get some another eigenvalue, and if we then again operate A operator on that state, then we will get the same eigenvalue we get before this operation, because this operation is not affecting this state B, right? This is not affecting, sorry, this is not affecting the operator A, right? Because then only we can get the same eigenvalue as we have got before. So we will use the same concept here for degenerate case, right? For degenerate case, if we do the measurement A initially on the A dash B dash, suppose it gives us eigenvalue A, and then if we then right, wait, now this is degenerate case, right? Means B dash state is not only B dash, I can express B dash or the same eigenvalue with the same eigenvalue. We have different, or we have linearly independent set of eigen vectors. Suppose there is degeneracy, suppose B have degeneracy of n, there are n linearly independent eigenvectors corresponding to a same eigenvalue. That means this state can be written like also A dash into A dash comma, this is suppose not dash, this is suppose 1 state, this can I write 2, the same this like this thing. All the things are possible, right? After the measurement of this thing, all the same, all the states are equally probable. That means I can express the state after the measurement of this like this, a linear combination of all these things, like mathematically like this, I equals to 1 to n, as the nth we had the degeneracy of nth order degeneracy, means nth degrees of degeneracy, okay, like this. Now if we sequentially after this measurement, if we sequentially do this measurement, right, that is B operating on the eigengate or on the system after the measurement of A, then what we'll get, then this will extract any one of the state, means it this have a linear combination of all the states like this, so it will extract the operation of B, will extract any one of the any one from the linear combination, suppose Bj, it will take Bj. That means things will be like this, and the summation will be not there, and this will give some eigenvalue, suppose B dash. Then again if you apply the operator A on this state, then what will get, then you will get again the same eigenvalue, right? You will get the same eigenvalue, because this operation like the non-degenerate case is again not affecting this state, the A state, and that's why after this measurement, when we measure A again, then we'll get the same eigenvalue as we have get before, right? So this is the concept of degenerate case, and this was the concept of non-degenerate case. So this is all what is meant by a computable observable, and this theorem is also proved, I think. So I have all the doubts concerning these computable observables is cleared, and in the upcoming videos I will also discuss some basic and very important core concepts of quantum mechanics, which is very much important. So for getting the notifications of that videos, do subscribe this channel and share this video with your friends. So take care of yourself. Thanks for watching.